Hello and welcome to the third lecture in chapter 21. Here at present we are doing this part, that is exploring correlations and multicollinearity in the data sets. The name of the chapter was Advanced Statistical Analysis. Now about exploring collinearity, we have seen about correlation matrix, and we also now know that before plotting correlation matrix you have to do one-hot encoding so that all categorical variables are converted into numerical variables. Then we also plotted heat map, and heat map, if you write annotate is equal to true, then in that case you will get the value of the correlation between each pair of the variable inside the small squares, and the color code as well as the value both will help you to decide the correlation. Now I also said that color code says that here, for example, closer to dark red means high correlation and closer to dark blue means high negative correlation, right? But the question is there any absolute high or low value? For example, in this particular data set, 0.68 and 0.60, that would be considered high correlation. But in that example, for example, here, that crop yield example, now you can see that there are certain correlation which are 1, 0.98, minus 0.97, 0.85, and so on. Okay, this is also minus 0.97, minus 0.71. So the question is here, should I consider this 0.52 as high correlation? So that means high or low is always relative compared to what are the highest possible correlations inside your data set between different features. So we would like to have some absolute measure so that we can say with confidence that if the value of this quantity is greater than this, then highly correlated, and value of this quantity is less than this much, then two variables or two features are not highly correlated. So the quantity which can help us in that kind of thing is called VIF, variance inflation factor. Okay, and it has some absolute measure irrespective of the type of data. Usually VIF is greater than 10, then we say that two variables are highly correlated, and VIF is less than 10, then we say that okay, correlation is there but that is not very significant. Okay, or you can treat those variables as independent variables. So you can here import the library. We have already imported, but I am testing that here where it is required, because so far we have not used this library, right? So far in the correlation matrix and heat map, that is not required. Now it is required, so I am pasting that here above this function definition. So from states model dot states dot outliers underscore influence, it is a little bit lengthy. Import VIF, variance inflation factor. But I have already taught you that states model dot, and you press the tab character, then you will get the hint about next states, then press the tab character, outlier underscore influence. So if you have done it 2-3 times, then as you press the tab character, you will see that among the options, and you will immediately remember it. Now once you import this variance inflation factor, we have already imported because our this line was in that the beginner the topmost cell which we executed, so it is already imported. Now we define one function, calculate VIF, and that function takes some data and gives one output, VIF underscore data. Now what is that VIF underscore data? Then VIF underscore data is equal to pd dot data frame. So that means this is just at present, this line just initiates or initializes one empty data frame. Now we are adding one column to that empty data frame, VIF underscore data, add a column named feature. What is that column? Then that is data dot columns. So that means that each time this function will be called, this data, whatever is supplied as the argument here, its columns will be added as feature, right? So calculate VIF for each feature. Then VIF data VIF is equal to, so next column which is just beside the feature column will be VIF column, and that will be given by variance inflation factor data dot values I. Okay, for I in the range, len data dot columns. So that means take all columns one by one. If there are 5 columns, then this variable len data dot columns will be 5. If there are 8 columns, data dot columns are 8 different columns, then this variable len data dot columns would be 8. And in that case, for I in the range 0 to 7, because when the range word is used, we know that it is 0 to 8, but 8 will not be included. So 0, 1, 2, 3, 0th column, first column, all the columns one by one will be taken, and their values are put here. Value of I would be put here, and the variance inflation factor will be calculated, and that would be actually placed in this VIF data VIF. So this is actually a list comprehension. If you see carefully, that is why I brought that line from the bottom to same line, because it now becomes clear that list comprehension is started always like that. I said that something initially you leave empty, and for I in the range, that len data dot columns, and then what you do is fill your list. Here you are filling this column of your VIF data frame. Empty data frame was created, first column was feature, and the second column is now you are filling that column with variance inflation factor data dot values for values of which column? Ith column. For I in which range? That is 0 to number of columns. So it will one by one take 0th column, values of that column it will use here, and find VIF, that will be filled in the list. Then it will take first column, where the values of first column will be put here, its VIF will be found, and that value will be put in the next feature, and so on. So ultimately we will get somewhat like this kind of data frame. The name of the data frame was VIF underscore data, but now it is no longer empty. Here it was empty, but now one column feature has been added, and that is equal to data dot columns. So that will have all feature names, and another column VIF has been added, in which the calculated values of VIF for the respective columns are there. So the output would look somewhat like this, right? So we will get this kind of data frame, because for VIF underscore data, this is empty data frame. Then first you have added one column feature F, here I am writing, and second you have added other column VIF, and for filling up that other column, that is that VIF column, you are using this list comprehension. So first feature with that its VIF, second feature with that its VIF, third feature with that its VIF, and so on. And how VIF will be calculated? Then that is calculated by this method. You have already imported variance underscore inflation underscore factor. So then variance underscore inflation underscore factor data dot values of ith column, where I will vary from 0 to, or that is len of data dot column, or 0 to number of columns, right? So that will vary from first column to second column. Suppose there are 4 features only, so then it will vary from 0, 1, 2, 3, and 4, like that. Okay, so then that is how the second column will be filled, and you should get an output like this. So this is the function. When you define the function, at that time nothing happens, only the function is created. So now you want to call that function. So for that, suppose I take this much in a new cell. So I want to call my function, and therefore I write numeric underscore calls equals df total bill tip size. Okay, so total bill, tip, and size, these are my 3 columns. So len of data dot columns will be 3. Okay, and that means this I would vary in range 3, 0 to 3. 0 to 3 means 0, 1, and 2, because 0 to 3 means up to 3 but not including 3. So 0th column will be taken, its VIF will be calculated, and it will be put in VIF column. First column will be taken, its VIF will be calculated, and it will be put in VIF column. This will be taken, and its VIF will be calculated, and it will be put in this VIF column, right? And then the function you are calling here, this is just deciding which columns you will pass to your function, so that you have stored as a numeric column. Okay, and then calculate VIF of numeric columns. So this is one important thing. Again, it shows that VIF can be calculated only for numeric columns. Therefore, if your data set has categorical column, then before calculating VIF, you should convert into encoding. And still, even after encoding, I did not prefer to use all the columns. I only prefer to use those columns which were right from the beginning numeric. That is the 3 columns in the DF which were right from the beginning numeric. So that is this total bill was numeric, tip was numeric, and this size was numeric. So I am taking only those 3 columns for calculating VIF, right? So if you take that, then you can see that total bill has 13 VIF, so pretty high. Anything more than 10 is high. Size 9.6. Even that is close, bordering with 10. So perhaps you can say that these 3 columns represent multicollinearity. Okay, so explanation of the code I have already done, but we calculate VIF for each numerical value, and VIF greater than 10 suggests significant collinearity, which might require remedial measures such as removing the variable or using PCA. Now in this case, removing the variable is completely out of question, because total bill you can't remove, tip also you can't remove, and the size of the group which comes for lunch or dinner, that also you can't remove. So the only option which you are left with, you will have to use principal component analysis. We have not learned principal component analysis, but whenever it will come, then we will see that it can handle this kind of multicollinearity very easily. Okay, so this approach to analyzing correlations and addressing multicollinearity helps in refining models so that the models are robust and interpretable. Okay, so that means this correlation matrix or heat map, they just help to detect the collinearity. But the question is similarly, but that is in relative terms. I told that in this data set, 1 is considered high correlation, 99 is considered high relation, and therefore this 48, 46, these are considered moderate correlations. But in this data set, for example, whenever 46 etc. would be there, now 46 I don't find anywhere. Yeah, here for example, this is 46. Then that would be considered a reasonably high correlation. So what is high and what is low in absolute terms cannot be known from correlation matrix or the heat map, but that can be known from VIF. If VIF greater than 10, either drop that column or express that column in terms of other columns or something. But that is use this PCA technique. Okay. Now that was about VIF and multicollinearity. Now the topic 2, if you remember when we started the chapter, at the time first topic was exploring correlation multicollinearity, so that we have done now. Now topic B, revision of Anova and its applications in Python. So very quickly we will go, because in chapter 19, this chapter, we have done much detailed discussion of Anova. So just a quick discussion about this Anova. So understanding Anova. What is Anova? Analysis of variance, that AN of, so this O, and variance, so this VA. So Anova is a statistical method that is used to compare the means of 3 or more groups to determine if at least one group mean is statistically different from the others. Okay, so you want to decide if the group means are different from the others or not, and it is especially useful for dealing with categorical independent variables which have 3 or more categories. So other hypothesis tests, they can deal with only 2 categories, for example 2 sample t-test or two independent sample t-test, but Anova has that greatness that it can handle 3, 4, 5, any number of categories in one go only. Another important test which can handle categorical variable is the chi-square test, right? So Anova and chi-square test, they are important. In previous chapter, that's why we did a revision of t-test and chi-square test, and here we are doing revision of Anova. What is its importance? It can help in comparison of multiple groups, which is more efficient and more informative than multiple t-tests. So for example, if there are 3 columns, then for t-test you will have to take 1 t-test for first and second, 1 t-test for second and third, and 1 t-test for first and third, 3 t-tests. And that is not very efficient. And second thing, even if you do it somehow, it is not informative, right? Compared to that, just a single Anova test with those 3 columns as 3 separate groups, and everything is clearly understood. Interaction effect between the 2 columns, that cannot be understood by t-test. In fact, the very basic assumption of t-test is independent sample t-test, while here there is no such requirement for Anova. In fact, it can help us to plot interaction plot. And in 19th chapter, those who remember, we have done much detailed discussion, and we even plotted the interaction plot for 2 variables. So those who are not remembering, they should first refer 19th chapter once again. How Anova works? Anova tests the null hypothesis that all group means are equal. Null always means the status quo or there is no change, while alternative hypothesis says that group means are different. So that means that the very mechanism of making 3 groups or 2 groups, that has caused some changes, which changes are responsible for creating a change in the means of the 2 groups. That is what the alternative hypothesis is. That just like t-test calculate t-test statistics, the Anova calculate F statistic, and from F statistic we calculate the p-value. Thereafter the thing remains the same. If p-value is less than alpha, which is 0.05 for 95% confidence interval, then we reject null hypothesis, and if p-value is greater than alpha, then we fail to reject the null hypothesis. So let us do the example of tips dataset. So same tips dataset, it is already okay. Let us import once again, and this is one extra line. Now this time I want to do one-way Anova test, so that is why I am using scipy from scipy.stats import f underscore one-way Anova, because Anova test is also called f test. It gives f statistics. Okay, then load your dataset and print your dataset. These are our usual steps, and now we know we want to study the effect of various parameters on the tip. So for example, if total bill affects the tip, so what you will do, you will take different groups. Say tip is equal, total bill is equal to 0 to 5, 5 to 10, 10 to 15, and then for each group you will find the mean value of tip. And if those mean values do not differ, then null hypothesis is correct, that there is no difference between the means. And similarly, if mean values differ, then you will say that total bill affects the tip. Here we will not take the effect of total bill on tip, but we will consider these 2 variables, tip and the day. So what will be our null hypothesis? That the amount which is given for tip does not depend upon the day of the week. Or in other words, null hypothesis says that the mean tip on Monday is same as mean tip on Tuesday, as same as Wednesday, same Thursday, same Friday, same Saturday, same Sunday. So all days the mean tip remains equal. That is what null hypothesis says. While alternative hypothesis says that at least one day has higher value of mean tip. Maybe Thursday or maybe Sunday, we don't know, but at least one mean tip is higher. Now, my problem with this data set is that it has separate entries for each day, but I do not have entire group of all Sunday entries, entire group of all Saturday entries, entire group of all Thursday entries. So we know that that can be easily done by using group by. And the best way to use group by is to use dictionary comprehension. So this is right side is dictionary comprehension. Always look at right side first, and then that left side just shows that whatever result the right side gives, that you are storing in this new variable. Now, in the dictionary comprehension also, we know that we first initially leave this part blank, and this is just a for loop. So for day, comma data in the df, so that means take this column, day and data in the df dot group by day observed equals true. So we are grouping by day. So that means that data is what? Data is my this column. I think I should write, okay, data in df dot group by, so that will work. Okay, fine. So that day we are grouping by day. So all observations of Sunday, that will be the first key. Then Monday will be, Saturday, that will be the second key, because day is given as a key. Thursday, that will be the another key. And the tip on that day, that is data tip dot values on that day, that will be the values in the dictionary. So what this dictionary will contain? It will contain 4 keys: Thursday, Friday, Saturday, Sunday, and it will contain the tips on those 4 keys as a list, because even on same day, Thursday, there will be many entries. Even on same Sunday, you can see there are many entries. So that means there will be many tips. For this record, the tip is this much. For this record, this much. So all those Sundays tips, whenever the key value here is Sunday, all the tips on Sunday, that will be in this list. Day on tip, that is tip column for the data dot values for day data in the df dot group by. So if you see this, then you will get this kind of data. That is what I wanted, right? So these are now my observations only of Thursday, and these are the tips on Thursdays. This is my observations only on Friday, and these are the tips on various Fridays. These are my observations on Saturday, and these are the tips on various Saturdays. And this is the observation on Sunday, and these are my tips for various Sundays, right? Now, these are 4 groups. So this is my first group, this is my second group, this is my third group, this is my fourth group. So these are my 4 groups, and I want to compare the mean of all these tips on Thursday with mean of all these tips on Friday, with mean of all these tips on Saturday, and with mean of all these tips on Sunday. And my null hypothesis says that there is no difference between the means on various days, and alternative hypothesis says that the means were significantly different. And for finding that, what I will do is I will put these 4 groups as the data to one-way ANOVA test. So F one-way and group data dot values. So group data dot values, and this asterisk means that these 4 groups will be supplied. So first group values means only values will be supplied, right? The key will not be supplied. So first group will be this, second group will be this, third group will be this, and fourth group will be this. So these groups will be supplied, and their one-way ANOVA test is will be performed. One-way ANOVA gives as the output 2 values, F statistics and P value. So F statistics should be large, and P value should be less than or equal to 0.05 for 95% confidence interval. Okay, so let us try to perform one-way ANOVA test, and let us so the F statistic is large, 1.672. Large is always very relative term, and nothing becomes clear, ambiguous it is, but P value is the deciding thing. Now P value comes out to be 0.1735, right? So that is pretty high value, and you can say that this is not obeyed. P is less than 0.05, that is not obeyed. In fact, my P is, so that means I cannot reject null hypothesis. So P is not less than, or that means P is much greater than 0.05. It is 1.17. So that is pretty large, right? So you can say that null hypothesis cannot be rejected, and cannot be rejected. So as a result, you will say that there is no significant difference between the tips which one receives on different days, right? Now, this is the result just printed. If P is less than this, then I would print this, but here my P is greater than that, so I would print that we fail to reject null hypothesis. There is no significant difference between the groups. So the mean tip, whether you find on Sunday or Monday or Tuesday or Thursday, the mean tip remains same. Now this example was used actually to study the behavior of customers and to arrange the staff shifts, because the waiters initially thought that in the weekends they would receive higher tips, and therefore there was a kind of fight between the staff that give me the weekend duty, and those who did not get the weekend duty, they found that actually speaking, they found that they are losing on tips. They felt it that way. But this experiment proved statistically there is no significant difference between the mean value of T. In fact, those who prefer to work on Saturday and Sunday, they had to handle large number of orders compared to those who worked on Friday, minimal number of orders, or even Thursday, reasonable moderate number of orders. So waiters must be compensated actually more on Saturday and Sunday, and you should not think that they are receiving large number of orders, so they will receive more tip, and therefore there is no need to pay them more. You should be compensate them more because they are handling very large number of orders on weekends, right? So that is what it is. But suppose this p value would come out to be 0.01 or 0.001. So in that case, you would say that P is less than 0.05, and in that case the null hypothesis will be rejected. So alternative hypothesis would come into picture, and alternative hypothesis which says that at least one day has higher tip on an average. Okay, fine. Now this is the explanation of course, so that we have already done. Now practical examples. One is this example, crop yield estimation. For example, this is the case. So these are the three fields of same size, same soil quality, everything else is same in these three fields. One green box, second green box, and the third green box. But the first field has fertilizer F1 use, second field has fertilizer F2 use, and third field has fertilizer F3 use. Now this is first field means not only one field but one sample. So exactly same size, 35 to 40 fields are taken. This exactly same size, but with different fertilizer, 40 fields are taken, and with third fertilizer also 40 fields are taken. So this is sample 1, sample 2, sample 3, and with three different fertilizers, the crop yields, yield 1, yield 2, and yield 3 were found. These are also the mean values. Okay, so that means this is the mean yield for the 40 fields with fertilizer F1. This is the mean yield for 40 fields with fertilizer F2, and this is the mean yield for all samples with fertilizer F3 use. In all other respects, the fields were same, area and weather and soil quality and everything else is same. Then I want to check if yield is affected by the type of fertilizer used. So null hypothesis will say that yields on three fields will be same. That means the fertilizer has no effect on yield. While alternative hypothesis will say that this y1 is not equal to y2 is not equal to y3. So mean yield for these three samples would be different. Say it will say that y3 is greater than y2 is greater than y1. So that means that this fertilizer is the best. This is the second best, and this is the worst fertilizer because it gives the poorest of poor yield, right? So this kind of experiment. Now the question is how to check whether null hypothesis is correct or alternative hypothesis is correct. So this is a classic case of multiple samples, 3 or more samples, and I want to compare the group means of one particular quantity. Here it is crop yield. I want to compare the mean of this sample with this sample with this sample. Then I will conduct ANOVA, and if I get p value is less than alpha, then I will say that no, null hypothesis is rejected and alternative hypothesis is correct. So that means that the fertilizer affects the yield. But if I get p is equal to 0.25, which is much more than alpha, so then in that case I would say that null hypothesis is correct and alternative is wrong, and then I will say that fertilizers do not affect the yield, right? So this type of experiments are done by both fertilizers company as well as farmers cooperative society, not only for the fertilizer, but you can make samples based on other things. Say here try seed 1, seed 2, and seed 3, or here try some that insecticides 1, insecticide 2, and insecticide 3, or maybe here you tried irrigation technology 1, irrigation technology 2, irrigation technology 3, and compare the yields. Sorry. So you will find which one is better, right? Now that is one application. Second application is in automotive industry, where vehicle design and testing phase are used to evaluate how different design modifications affect. Here also in design you can change so many things. For example, you can try engine 1, engine 2, engine 3 for the vehicle, or you can try tire 1, tire 2, tire 3, three different brands of tire. Okay, then you can try suspension systems 3 different brands of suspension systems, and you can determine some performance matrix, maybe which gives higher fuel efficiency, mileage, or which gives more speed and durability, or which is more comfortable, ride, like that. So anything, just like here you are measuring yield, you can measure mileage or something, and then you can decide whether changing the engine type affects the mileage or changing the tires affect the mileage, and so on. Okay, so this is one more application of ANOVA. Fine. So after this we will continue with this non-parametric test, and it is going to be a very small discussion, and then exercise questions are there. They are also exactly in 3 parts. First part this, second part about ANOVA, and third part is about non-parametric tests. So exercise you will do, but this part I will have to discuss non-parametric test. So that we'll do in the next lecture. Thank you.